Thank you for inviting me and introduction and opportunity to talk. So hopefully I'll be able to tell you how to see things that you like to dream about, but you also see that in this part of this talk we have to dream too, and in order to interpret what we see, right? And do a lot of theory. So before I start, I want to acknowledge actually my collaborators. So just to tell you how our dreaming sometimes can be costly, I think we first took this interesting material that I'll be talking about was discovered, or at least the first paper, and where it was acknowledged, it was in 2007 by a group of Ian Fisher, where he acknowledged how interesting this material is. Then it followed in 2010 by interesting theory of group of Leon Balance about, what is this physics about? I want to find the, and so 3 years later, and then I think we did our first experiments in this in 2014 or so. So this is how long it took us to do actually NMR, and then 4 years to interpret the data. So, it takes a long time to dream about it. And I want to thank actually all of my students in a group. Rong is actually here. She'll be giving a talk on Thursday about a lot of calculations. And Eric, and it all started with Lulu and Van Kong about 5 years ago. And also my colleague, Brenda Rubenstein at Brown, who helped us a lot with some first principal calculation. And then a lot of the work that I'll talk is evolved, and Samuele will talk after me, so on other aspects, but this is where we start. And then Cesare, that is helping us figure out in all these complicated things now what this means. So this is the talk about stuff that we know from before. So anyway, okay, we all know this, right? We start the lesson. What happens when you take a simple metal and you add correlations, and you can solve the Hubbard model and actually obtain that you get this Mott insulator state here, insulating state that cannot be explained by band theory. Now, what is interesting, and I'm sure that everybody working on spin-orbit coupling has seen this graph here from a review paper quoted here. What happens when things are pretty boring, right, for us when we just have correlations, even though we don't really know how to solve this correctly. But then when you add spin-orbit coupling, you get all other level of complexity. And this is what is expected here. So this is spin-orbit coupling and all these exotic states of matter. And what we're actually going to talk about is really this regime here. So what happens when you kind of have comparable value of spin-orbit coupling? So of course, when you have weak spin-orbit coupling, then you can always do perturbation and things are not, or you get topological insulators, but that's not what we're going to talk about it. So what happens when, correlations are strong and also spin-orbit coupling is strong here? And as an experimentalist or doing NMR and have to probe the spin directly, I like to basically say, well, spin is not a good quantum number. So if I just want to do a simple experiment with some kind of resonance and flip the spin, well, I don't know where that is, right? And actually, it turns out that it's a very good thing to work with the nuclear spin. So this is a rare example where in this any spin-orbit coupled material is actually very good to do NMR. So nuclear magnetic resonance, not as a chemist to do the structure, because really we know the structure from before, we don't care about it. But because the electronic spin is actually, so to speak, it's coupled, it's entangled with its orbital motion, therefore not a good quantum number. It turns out that the nuclear spin, what we realized during this entire work for years now, that because of the nature of the coupling through this hyperfine interaction that I will talk about it on site, only couples to spin degrees of freedom. Okay, so it's almost like experimental filter for spin part. And then, of course, there are effects of all this other stuff that happens, and hopefully I'll show you how we see that. Okay, and so because of this kind of coupling, spin-orbit coupling, what you actually need is to really use these local probes so that somehow you can actually couple to the spin part. Not that that's important, but that actually, I guess, makes theories more, easy if I tell you what is important from the spin part. And the material that we want to actually start to, so to get this physics, right, interesting physics where we have both degrees of freedom on a comparable scale is, well, we're going to actually deal with these 5D transitional metal materials. And anyway, this is a list, again, a laundry list from this review article of what are all these interesting physical states that one can get. And if you are applied physicist, I know most of you do theory, so you don't really care, but this is actually pictures of all the beautiful things that practically, that, you know, my colleagues who actually work on applied physics and can get a lot of money. See, it's a review article that just came out. All the beautiful devices and stuff that you can actually make if you can control spin-orbit coupling. So I guess all of our work is very useful for them because, you know, if we tell them how to control it, then they can make all these useful devices out of it. So, and let me go back to physics now. So this is the material that I'm going to actually use. And, you know, it's one of those things that as an experimentalist, you get lucky. It just has everything the right way. And from theoretical point of view, it really allows you to probe this regime here. So it's barium 2 sodium osmium 06. So it's a double perovskite. At room temperature, it actually has a perfect cubic structure. So it's actually FCC lattice, so 2 cubic, and I'll tell you also experimentally why we believe that that's so. And it has unpaired 5D1 electron that is actually supplied by osmium. It's a really Mott insulator. I mean, insulated in real sense of the word, even from Ian's Fisher. So basically, if you do optical reflectivity, you actually see that it's a true insulator. And ions are very well separated from each other. And so I guess just to kind of, I don't have to go into the details, but as I said, the material was interesting, and then there was this theory that was proposed by what really matters, or how to, in a group of Leon balance, what do you have to do to basically describe the magnetism in this kind of system? And simply, you know, not to go into details, because this is an experimental talk, is to, what really matters is that you have these anisotropic or multipolar spin couplings, okay, that are presented here. One thing that there were actually two clear predictions of this model. It's a mean field theory, so of course, you know, not the exact solutions, but one of the predictions in that paper was that local spin expectation values are different from the average ones. So if I probe the magnetism locally, I should find different values than what I do, you know, measurement by squid or any average. This is really weird, right? That normally doesn't happen, that you can see that. And then that there is also a structural change, which basically, to speak the theory language, that there's some kind of a quadrupolar order that actually establishes itself. So what one should see is that there is a local structural change, not the global one, that precedes the magnetism, okay? And so this is what we, you know, wanted to probe. How do you do this? Well, you need a local probe, and you also need something that can probe both magnetism and kind of orbital degrees of freedom at the same time. And so really, I'll show you how in this particular case, the NMR actually was really an ideal probe because, yeah?
Sorry. What is the measured band gap?
The measure, no one has actually.
Oh, I thought you said in Fisher.
In Fisher's paper, how many EVs wrong was it measured? They did not measure they could not measure the gap. They just saw from the conductivity that it's truly an insulator. But there are speculations about it, what the gap was.
So you have two GZ state on one data site, XY, yes?
Yeah.
Yeah. But maybe it's possible to put them together. And
That's fine. I'll talk about the experiment. Okay, I'll just put this, what he said, you know. Nobody says that this is the right, the whole point of what I'm going to talk about is to test whether this is the right approach, right? I'm not commenting about the theory, whether this is the right way of doing things or not. Just saying, you know, this is what he proposed. Basically, experimentally, there were two things that we were after. And that's it. I'm not saying it's right or wrong, right? So.
Yeah, I don't know what you mean there when you write not found in DFT-based calculations, distinct prediction of the quantum models not found in DFT-based.
No, back in the day, what I mean, at the time, okay, 2010, okay,
1/2, is Z of 1/2, then GZ squared 1/2 will be 1. It's 1/2.
What I'm trying to say that all the calculations up to two.
That's the point that
No.
it's not necessarily.
The point is, in that time when this paper was published, 2010, right? There were other things, for example, from the, it was predicted that it's all discussion. What is the right way of doing? And you could not find, for example, you find that the system it remains cubic. Okay, that's the only thing I'm saying here. So what is meant is that the system is. These facts, these facts.
If there are questions, we can raise our hand and discuss gently, but all this whispering around might
It's a question to notation.
Okay.
So we can go into that later, okay? And what I'm saying is basically 2010, let's go back in time when this was proposed. Basically, this was these predictions are quite unique for this particular model. And the only thing that matters, again, that you have this anisotropic, this kind of anisotropic couplings, okay? Whether it's right or not, and I'm not going to even go into detail. I just want to tell you why this whole, experimentally now, why this was proposed. So experimentally, there are two facts here that are quite bizarre, okay? And why people actually study this. So first of all, if you look at this paper, specific heat, there are actually much nicer measurements that came out this year. See, there's some anomaly here, and turned out that, that if you do a very careful measurements, and Ron will talk about it, you actually see that this is real. And it's kind of consistent with what we saw. But there is a missing kind of entropy. So for example, at this beautiful specific heat data here, right? It's a textbook example of kind of lambda phase transition. If effective spin is 3/2. That's what you get just if you, count electrons, right? It turns out that the magnetic entropy at the transition is actually R ln of 2, okay? And so where's this missing entropy? Why it experimentally looks like the system is spin 1/2, right? Even though, if you just do a simple counting, it turns out that it's 3/2. And more importantly, easy axis, right, for magnetism, right? If you see, magnetization is maximum in 110 direction. So it looks like it's a ferromagnet. It's a cubic crystal structure, and you have ferromagnet where easy axis is along diagonal of the cube, right? And that's not what should happen, in Landau theory. Not that I know I'm expert of it, but exactly. And if you look at actually, at the paramagnetic state, the interactions are antiferromagnetic by. Right? Curie-Weiss is a negative temperature.
But
So,
magnetic over there.
yeah. And so let me tell you what we see. Now, this is all, again, this is magnetization measurement. So it's an average. It's a bulk magnetization measurement, right? So what is it? What has been seen in a local, and I'll give you a preview of what we see by NMR. Okay, so that was the results of, other measurements before we started. So we actually see, this is going down to cold blue. As a function of temperature, what we see that we have locally, and I only stripped everything except these yellow guys, it's a sodium, where we choose to do our NMR measurements on. You see a perfect cubic state, and I'll show you why I claim so. And as you lower the temperature, before magnetic state onsets, actually, so this is a phase diagram of field versus temperature. So paramagnetic state, which is perfectly cubic, okay? And then you see this broke state in which locally the cubic symmetry is broken, okay? And it's, it looks like it's paramagnetic. There's no magnetic long-range order. And then as you lower temperature further, you actually get this state where system orders ferromagnetically, but it has two sublattices, okay? And the lattice locally has this orthorhombic distortion, so it's not cubic. Now, there are people who have actually calculated and show that it can actually happen. That is because of the double perovskite structure. If it was a single, you could not have this kind of local distortion. So, if you look at globally, the lattice actually stays cubic still. Okay, and so let me show you how we can, do this and how we probe. I guess that's the most important thing. Then we can argue about interpretation, right? So what we probe in NMR, you can do NMR spectra. This is what I'm going to show you today. is that we probe the internal magnetic field, or if you wish, a projection of the internal magnetic field along the direction of the applied field. And so we probe this kind of a probability distribution of the local fields at the sodium site in this case. And what I mean by the local field, in this example, everything else is negligible, but it's really the field that is created by osmium electrons here, the free electrons of osmium. And they're coupled through this hyperfine interaction. So it's an overlap of the wave functions, right? And this thing here is a tensor, right? And basically what one sees, okay, these are kind of cartoon pictures of what you would see if you have a simple ferromagnet. So these arrows here are, again, electrons, right? These are electronic spins, and you can imagine that next to each electronic site, there is a nuclear site sitting right there. So it's a ferromagnet. Things are very simple. This is kind of the resonant frequency where your nuclei would resonate if it was in, vacuum, right? Meaning it would just oscillate at that particular magnetic field where you applied. And then this shift is proportional to this local field that comes, extra field that these electrons provide. If you have an antiferromagnet, you can imagine that all of these would give you, right, kind of one line shifted to the positive side from this zero, and then all the blue guys, right, these are the electrons pointing in the opposite direction, they would shift the resonance to the negative side, okay? If you have commensurate or, orders, well, this here is a probability distribution of, a sine or cosine function, right? A trigonometric function, and that's what you would really measure, okay? So there's another thing here, a beauty about, and this is something that it's less commonly known, and that is that for any spin that has a spin greater than 1/2, this nuclear has a quadrupolar moment. And in actually that quadrupolar moment, interacts with the electrical field gradient. Again, electronic currents, field gradient, or charge distribution. And that interaction gives you basically, of course, if you have a cubic crystal structure, then, electrical field gradient is just 0 in a cubic symmetry locally. There's no gradients. And this interaction would then be 0, right? There's no interaction. And if you break the cubic symmetry, you can generate electrical field gradients or not, right? It depends. And then you start to see, of course, depending on this line width here or this, what you do see is actually, let me just talk about it when you generate sufficient electrical field gradient. What's going to happen is that the normal NMR line would split. There's an extra interaction, which is square in a spin moment. And you would actually obtain, so for example, for sodium, we have spin of 3/2. And here you would actually obtain 3 lines, 3 extra lines that come from that interaction, okay? And so this splitting between these 3 lines here, this is kind of just the energy level if you look at it in the details of this interaction, that splitting is actually directly proportional to the electrical field gradient. And so, there's math of all of that. So this is that Hamiltonian, and what matters really that it's proportional to the spin number square, so you can work out all the energy levels. The bottom line is that the splitting between these lines depends on, okay, quadrupolar moment, but that's what it is, right? So, nucleus is not symmetric. It actually has that moment, and then it interacts with the electrical field gradient. This VZZ is actually a principal axis of that electrical field gradient. And it acts almost as a magnetic field, right? So it's a quantization axis. It's not a magnetic field, but it's basically this principal axis of the electrical field gradient. And so if you do an experiment where you actually, rotate the applied magnetic field, which polarizes the nuclei, you can figure out through rotational studies where this axis is inside of the crystal, just by simply rotating the field. And so the magnitude of this quadrupolar moment, as I said, the magnitude of the splitting when we measure gives us direct measure of this electrical field gradient, right? Remember, it's 0 in a cubic symmetry. So if you break cubic symmetry, you can actually see the splitting of the line broadening, okay, in this case. And just to show you that this is really what we see in our data. So at high temperature in this paramagnetic state, right, there's nothing. It's a cubic symmetry. and the state is paramagnetic. There are no magnetic moments, so basically you just measure this super narrow NMR line. It's very nice and narrow, clean, which means your crystal is perfect. It has a perfect cubic symmetry. And you start cooling down, right? So locally, this is my sodium. It just sees basically perfectly cubic symmetry here. Electrical field gradient is 0. And that's why you see such a nice, beautiful line. And as you cool down, as you see here, it's quite obvious, it starts to broaden. So as you start developing this electrical field gradient, sometimes it's not sufficient enough, right, to cause this obvious splitting, right? It's within, as we say in experiments, right, within the line width, right? So it has to reach a certain level so you can actually distinguish this, right? It starts to develop. And you can see here how it starts to split. So I have almost here, I can actually discern basically 3 lines, which means that I'm starting to, something is happening in a sample, you're starting to generate finite electrical field gradients, meaning you're breaking locally cubic symmetry, right? And then, and these are kind of these cartoon pictures that basically these, in the simplest picture, you can have these, this is oxygen here, octahedra, around this sodium. Red is osmium, which carries magnetic moment, and you start to actually distort these octahedra. That's the simplest possible thing to imagine. And what's important to note is that here I can actually discern 3 of these 3 lines. And then as you cool further down, look, I have very well developed triplets, right? So I have 3 lines here, I have 3 lines here, but there are 2 of them, right? So these are magnetically inequivalent sites. So basically this sodium here sees a different local field than this sodium here in a lattice, right? From 2 sublattices, local magnetic fields. Now, the reason why I know that is that one simple thing, if you remember, it's something, and I'll show you in the next slide. The reason why I know that, one is magnetic and one is not, it's very simple. All you have to do is change basically the value of the applied magnetic field. And then you can verify what's magnetic, what's not. So just to kind of show you, there are 2 things you can do, right? So I want to convince you that, the fact that I see 3 things here comes from this breaking of the local cubic symmetry. So if that's indeed so, then there are 3 things that have to happen, or 2 things that have to happen. So first of all, if you analyze this Hamiltonian and you look, as I said, it's the direction of this electrical field gradient, right? Or direction of the breaking of the symmetry that we can determine if we do the rotation. So if we rotate the applied field with respect to some crystalline axis that we know, right? Because this is unknown. We're trying to figure that out. And so you work out the math, and it tells you that if you have this quadrupolar interaction, this splitting, okay, right? So the distance between these peaks, right? That distance has to have, the following dependence on the angle between your crystalline axis and the magnetic field, okay? Also, this splitting has to be applied field independent, because it comes from, distorting these creating electrical field gradients, right? It has nothing to do with the applied field. This comes from orbital degrees of freedom, so to speak, right? From the charge density or some distortions of the charge around my sodium site. And so basically we have measured this, splitting. So if you look at this, what I call delta, right? It's a splitting between these satellites. It's the same, between these 2 and same between these 2. It's same on the other site as well. And we have measured anywhere from 5 Tesla to 37 Tesla, and we never saw a magnitude vary, right? So it's completely field independent, up to 35 Tesla, maybe later. And also this, angle dependence is such that it tells you that this really has to come from the creation of electrical field gradients. So really broken local symmetry in our sample, okay? Now, Rong will talk more, but again, if you do the analysis of this and Hamiltonian, it's a very simple quantum mechanics. It will actually, if we rotate the magnetic field within different axes, right? So you can take a cube and you can rotate in plane. You can also rotate along the diagonal of the cube, which we know, right? You can also rotate, in this direction as well, in these. And depending on what you find, that will actually tell you exactly where, again, these axes of the electrical field gradients are. And so that's indeed what we have done. We have done all these rotations, and it tells us basically that, what we figure out that the electrical field gradient, principal axes coincide with those of the crystal, and Rong will talk more about it on Thursday. And what we also found by comparing these rotations, again, along the cube, along the diagonal and along the faces of this cube, it basically tells you that at low temperatures, by analyzing, again, the angular dependence of the splitting, is that these distortions are orthorhombic, okay? Now, you wonder what breaks the symmetry in a crystal, that it's cubic. How do I, what do I mean by orthorhombic? I mean that, basically this is my c-axis that I've decided. It turns out that the way we define the c-axis is that you take your perfect crystal, your cube, and C is whatever it's normal to where we glue the sample. You experimentally put the stress on a sample in one direction. And so orthorhombic means basically in the plane of where you glued your sample, where you actually put the stress, physical stress on your sample. That's probably what, and we have done this along many different directions of our crystal, and, it always coincides with, C's, distortions are always orthorhombic, right, in a plane.
That you glue at one temperature and measure at the other. That's why there is strain.
But there's always a strain. Look, it's just enough to put, physically, it's enough you touch it with your fingers. You have grease on your fingers, okay? And it's you have to glue something, to put it, make sure it doesn't slide out. So usually it's vacuum grease. That's enough to give enough stress. And we believe really this is what creates this, all the three axes in a cube are equivalent. So, what do I call orthorhombic? It turned out experimentally.
You glue and measure at the same temperature or a different temperature?
Well, no, you pack everything at room temperature. You have to cool down the stuff. Okay. So I'm saying every time we take the sample out and we glue along whatever, we can recognize, where the diagonals we know.
Then it's not a mystery. Then it's well defined, right? You glue it at room temperature,
yes.
Then there is some thermal expansion.
Yeah.
So you pull it down, and then
fine.
Obviously the substrate squeezes.
No, but you have to, no, wait, it's different. No, because if I did the diffraction, okay, I would still find that the sample is cubic, okay? This is local. All I'm saying locally, what I call a c-axis here is that it's the axis, which is perpendicular to the face of my sample, where the applied field, okay? So this is local.
Your red arrows, that's tetragonal effectively, right?
Yes.
What is orthorhombic action? Your green arrows?
No, what I'm trying to show, so it would be basically tetragonal. There is distortion here.
Red is tetragonal. Green.
Yeah, green is, yes. So what I'm saying is that what we actually see is that in a this is what I call a c-axis where my field is up, right? And then it's in the plane perpendicular to that you have orthorhombic distortion. It's not the same. And again, I can figure that out from the rotations, okay? Yes, yeah. And it's local. What I mean by local is literally this octahedra of the oxygen around my sodium site, okay? Where the
lattice parameter,
yeah.
but rather
The direction A and B.
Yes.
rather the dimension
It's
of
a dimension
the
of
osmium oxygen 6 octahedra.
Yes.
The system is cubic.
Cubic.
You can't tell that, right?
yes.
Okay, so
Can
it's
you
cubic
estimate
plus
what's the size of the storm?
Yes. And my Rong will talk about it. Yes, the size in distortions are never exceeding actually 2%, actually 0.8% of the lattice, of the original lattice, okay?
But that's a normal distortion. That's a very, very large
Local, right?
Whatever. It's very
Fine.
large distortion.
Yeah, it is. It is. Oh, it's oxygen. You can't pick this up in X-rays, right? Or actually, they have seen it in,
So probably this is because of the way you are doing the experiment.
No, I'm saying that just serves to me. I think this is there regardless how you do it. It's just that I, yeah.
Put it into a glue.
Yes,
you think it's-
It's just it allows me to determine. And Rong will talk about this. I don't want to go into details, but this is what we identify, that this is Q2 distortion mode of this. If you actually do really not a fancy calculation starting for anything, but we actually use our experiment as a constraint and just do absolutely minimalistic models that would explain the experiment, you find that this is basically, Q2.
Immediate question, when you do DFT calculations,
Yeah.
you optimize the structure. Does it optimize into lower similar structure or not?
She will tell you this later how we do, because yes, and we,
If it's dynamic,
No, no.
then you will get static and slightly
no, we'll see. She'll talk about how do we do that, where we use our data to impose constraints on, because I'm not, and data is very clear. What you see after our experiment, actually in inelastic X-rays, they had to refine to have seen the same distortions. It was after.
In your previous slide, there was something written that pure tetragonal may also work.
Yes, I'll tell you why. Yes, because I can tell you, for me to figure out whether it's orthorhombic or tetragonal, what we need to do is do these rotations and study the splitting as a function of the angle. Now, if you look at the data here, right, I cannot really discern, right? I don't know. I mean, I can kind of know what it is. So I don't know the exact splitting. I cannot do this. So tetragonal could work basically here in this state, okay? Here, where I see the exact clear splittings and I can analyze as a function of angle, it's clear that it's orthorhombic, okay? That's why. Actually, X-rays have found at these temperatures that this is tetragonal here, as a matter of fact, after our...
Orthorhombic.
At high temperature, they found tetragonal, orthorhombic at low temperature, okay? So after our experiments, okay?
Or compressed? Tetragonal elongation or compression?
I don't know what exactly, because this is not published. I only know that they've been looking for it for years, and only after our measurements, they found it. And I will actually just say one thing about it. I want to talk about the magnetism. Again, look at these triplets. I told you this is all magnetic. So what we can actually do is take the average field, right, on this triplet, average field here, and call this uniform magnetic field. This is how it looks as a function of temperature, okay? Develops, and then the difference between is a staggered field, right? And this is how it looks. Onsets at some temperature where the magnetism onsets, and you see it's completely field independent. I will tell you that, just kind of because I'm running out of time, we can discuss this because of this, is that, this is the data, the open symbols is what I showed you from the paper of Ian Fisher's work at the beginning, right? So magnetic moment, average measurements. Uniform field extracted by NMR is the same thing. I mean, theoretically, is the same thing. And this is what we find. I've never seen a system, okay, fine, here, maybe we don't have the same goniometer and angle, that's questionable. The point is that this direction here is not, the maximum for us. It's just, it's equal to that, okay, what we found in NMR. And so what we can actually do is, we have done very careful simulations. So, what you assume, that's your sodium. You put magnetic moment on this osmium, okay, treat it as just spin 1/2. And I'll tell you why I can do that. And then you actually simulate what, the NMR spectrum that you see, or the fields, is basically given by this stuff here. You treat this as a fitting parameter. We know what the moment is. And you try everything to try to actually explain all these angular, how does what you see vary as a function of the angle, again, between applied field and your crystalline axis. And there is only one, and that allows us to kind of, really figure out where these osmium moments are oriented, what direction. And this is what we found, that the magnetic state that explains actually our data is the following, is that you have two sublattices, you see? So it's ferromagnetic in each lattice, right here. You have all the spins are pointing in one direction. They're ferromagnetic. In the next plane here, they're pointing in a different direction. It turns out that, again, we treated this angle as an experimental parameter, figure out that they are canted, so along this direction, 110, okay? And they're actually, this angle is huge. What we found is about 65 degrees, okay? Now, this is the reason why you see so when they did the magnetization measurement, they said, oh, there's a small, or even μSR, they found a small moment magnetism. So the moment drops to 0.2. And the reason why it's such a small moment is actually that it's canted by such a large angle. Now, all the theories here should object to the fact that, I don't have time for this, but they should object to the fact that, how do I treat this, complex spin-orbit coupling when you don't even know what the spin is, as a spin 1/2. So therefore, all this simulation that I discussed of the fitting is bogus. Well, this is a beauty. This is where all the complexity goes into. So if you look at any book on magnetism, they will tell you this hyperfine coupling, has to reflect the symmetry either of your lattice, right, the local point symmetry of the lattice, or of the magnetic state. And, this is the hyperfine coupling tensor that we find in a paramagnetic state. It's diagonal, of course. It's a cubic crystal, right? And then, when we cool down, right, because of this complexity, or maybe even what, Leon predicted, that we should have this orbital order that accompanies this, that basically what he predicted is that what he said, that if you find these two sublattice ferromagnet, that's a proof that there's some kind of orbital order, staggered orbital order that accompanies this. This is what, breaks this cubic symmetry and so on, that precedes this magnetism. Well, if this is true, if my spin density looks like this, is some complicated cloud, right? All of that complexity is here, okay? And we treated this as a actually fitting parameter. This is what we found. So look, constraining these diagonal elements to be absolutely the same as in paramagnetic state, this is what we had. This thing has no symmetry. This thing is as complicated as it can get, right? And this is the statement why I said that we always neglect this. It's just kind of, annoying thing. But I think this is very important quantity to actually, this tensor gives us information about the complexity of this spin-orbit coupling. And what goes to a nuclei only is really the spin part. It allows us to basically, treat the moments. And again, I'm waiting for Cesare to, calculate this for us, and hopefully this really means something. I think there is a lot of information in there about the complexity of this system. And as I said, my student will talk about this, more calculations of what we found. Again, using this as a constraint to just very simple DFT calculation, we find that indeed you have to have this staggered orbital order. So hopefully, all of our data basically says one thing, and then that is, I'll stop, that really these multipolar interactions are the key to treating the physics of this material. So, thank you. Sorry, going over time.